Hi Year 10, we're going to go through the next bit of rate of reaction today, which is, as it says on the screen, surface area and rate of reaction. So if you can pause the video to get that date and title written down. However, the first thing we are going to do is to go through just a few bits of feedback for the graph that you drew for the assignment on temperature and rate of reaction. So make sure you've got the date and title sorted, find that graph, and then press play. Okay, so just a little bit of feedback on the graph that you drew from the Oak National Academy lesson I set for temperature and rate of reaction. I've given some feedback individually. I'm in the process of, I haven't quite finished everybody's yet, but I thought I'd give some general feedback first. So I've got a graph on screen at the minute, and this looks a little bit similar to some of the graphs I got from people. So have a look and see what you think might be wrong or needs to be improved about this graph. Well, the first thing that you might notice is it starts at 0. We've got all this space that we don't necessarily need just here. You could get away with starting 20 here and going 20, 30, 40, 50, etc. However, we are using enough space. When you're given a piece of graph paper, your plotted points have to cover at least 50% of the paper in both directions, which this does, so that's not a problem. One of the main things that's wrong with this is the line of best fit, and we're going to talk about that in just a second. And also a major issue is that there's no axes labels. So that's the first thing I'm going to do. So here I have the graph that's slightly corrected. I've taken away the line of best fit, and we'll look at that in just a second. But I have added axes labels. So on the y-axis, we have the dependent variable, which shows time taken. In seconds, must make sure you put the unit there. And on the x-axis for our independent variable, we've got the temperature, which is degrees C. Now, when it comes to this line of best fit, it's something that people find really tricky. Now, I know that in maths, a line of best fit is always straight, no matter what the data shows. But in science, our line of best fit needs to show the shape of the data. And what we're going to see in this topic and actually start to look at today is that the shape of the curve is very important and tells us about the science. Now, if you look at this data, there is a curve, and I know it can be a bit difficult to see. So what you can do is, if you get a ruler, what we're going to do is we're going to line the ruler up with the first and last point, absolutely first and last. So that's what we're going to do now. So there's my ruler lined up with the first point and the last point in our data. And what we can see is that every single point of our data is on one side of the ruler. And this, I think, just helps you to see that curve a lot more easily. Now, what you also have to do is you have to draw the curve freehand, and that is quite difficult. So I often find that actually turning the graph upside down, if we've got this kind of curve, is easier. I don't know about you, but drawing a curve going down that way is quite difficult. However, naturally, you tend to have an easier time drawing it going upwards just because of the natural sort of pivot of your hand. Now, this is something that we will do more of when we're back at school, but we will draw a line in just now. So I've got that line going through most of the points. What we might notice is that it doesn't quite go through all of them, and so I've missed this one out. And it is really important that we have a smooth curve. Now, we could miss out the top one, or we could miss out this second one, but by missing one of those out, we've got a slight anomaly, but not quite, because it's still touching the line. But it just means that we have a smooth curve. This one here could be an error with the recording or something like that. But it just shows that our data is not perfect, something that we will talk about in later lessons. So moving on to look at surface area. I'm going to use a few silly little examples because we're not able to do practicals and stuff. So I've got here a lollipop, and if you were to eat this lollipop, you know, how long would it take you to eat it? Well, if you were just sucking that lollipop, it would take you quite a long time. But what about this lollipop? That one would take even longer. So how could we eat these lollies quicker? Well, one way of eating these lollies faster would be to smash them up. And I know that some of you, if you were to eat a lolly, would probably crunch it with your teeth. But we could break it into small pieces. Now, this lesson is all about breaking reactants into pieces. And I know lollipops are a silly example, but it does sort of help us explain this a little. So another real life example here, I've got a potato that weighs about 200 grams. Would it cook quicker if we cooked it as a jacket potato and just shoved it in the oven as it is, or if we cut it into chips? I want you to have a think about which answer you think would be quicker, jacket potato or chips, and why. Well, if any of you have done any cooking, you might know that a jacket potato takes at least an hour to cook if you just put it in the oven and don't microwave it first. But if you were to cut that same potato into chips and had 200 grams of chips, it would cook a lot quicker. Now, if you think about the reason why, it's all to do with heat conduction, and this does tie into what we're looking at today. The heat from the oven can only conduct from the outside of the potato inwards. So the inside of the potato can't heat up and cook until the outer layers have done the same. And I've got a little animation just here showing a Bunsen burner modelling heating up a metal bar. So as we can see here, it starts to heat up, and as the particles heat up, they gain kinetic energy and they wiggle around more, they vibrate more, and they bump into the next door particles. And so this heat can only conduct because it is passing on that kinetic energy as it goes down. So if this end is the inside of the potato, it has to wait for the heat to travel through. Now, we're not talking about heat today, we're talking about surface area, but this is kind of the same idea. So basically, to put this very simply with our potato, cutting the potato into chips makes the inside turn into more outside. Now, if we were in school, or if I could get my camera working properly, I would do a demonstration. And what I would demo is 2 beakers of water, warm water, and jelly. And in the left-hand beaker, we have got 1 cube of jelly. And this is if you were to go to the supermarket and buy a packet of jelly that you have to dissolve in water before you then put it back in the fridge to let it set. So this is undissolved jelly straight out of the packet, just 1 cube in a beaker. And then on the right hand side, I've taken that same jelly cube, but I've cut it into 8 equal smaller cubes. Now we've got the same mass of jelly in each beaker and the same amount of water. Now, if we had this warm water and we put it on the jelly will dissolve. It will dissolve into the water. And the reason it does this is that the jelly dissolves as the water molecules collide with the jelly cube. But the water molecules can only collide with the outer surface of the cube. So the water molecules collide with the outside of the cube, dissolving that outer surface, at which point the water molecules can get to the layers of jelly underneath. Now, cutting the cube into smaller pieces means that we have more surface available for the water molecules to collide with. And if there's more surface, there will be more frequent collisions. And this might be sounding familiar if you think back to our collision theory lesson. Now, if we were doing this demo, we'd see this happening. The jelly cubes on the right would dissolve more quickly than the jelly on the left, and it would take longer for the whole cube to completely dissolve and form a solution of jelly than it would on the right. Now, I've mentioned this already, and it is the title of our lesson, but the outside layer of an object, substance, reactant, is known as its surface area. So here I've got a cube, and this is a little bit of maths, and apologies if this is telling you stuff that you know already. But we can unwrap this cube so that we can see the surface area more clearly. Now, you're probably very, very aware of this from maths, even down from primary school, but what we've got here is a net. So this is an unfolded shape, a 3D shape, and we can see this now in a 2-dimensional way, and it makes it a lot easier to see this outside layer of an object. Now, if we wanted to work out the total surface area of this shape, we would need to work out the surface area of each of these individual squares and then times it by 6, which is how many there are. So what we can see on screen here is just a sort of modelling experiment of surface area and particle collisions, and it's very similar to the simulation that you did for concentration and rate of reaction a couple of lessons ago. Now, this isn't going to do this in a particularly accurate quantitative way. We're not going to we can't say that the surface area has doubled. This is going to happen in a 2D fashion. So we just got to kind of imagine that these are almost like snooker balls on a snooker table, colliding with an object in the middle. This is going to give us a good idea in just 15 seconds of how increasing surface area does have a large effect on the rate of a chemical reaction by increasing the collisions. So as I press play, what we can see is that the particles are colliding randomly in all directions, and that we have more collisions happening in the same time than we do on the left hand side. And the only thing that is different is the surface area of the substance. We can see that there is a vastly increased number of collisions, 309 to 69, when we compare the larger surface area to the small surface area. Now, to look at this a little bit more mathematically, we can actually calculate the surface area as I mentioned earlier. So here we have a cube, and just in case you forgot what a cube looks like, I put a picture of dice on the screen there. That probably wasn't necessary. But if this cube was 2 centimeters by 2 centimeters by 2 centimeters, we can work out the surface area. So that's what I'd like you to do at the minute. Can you please just pause and calculate what the total surface area of the cube would be if its sides were 2 centimeters long? So hopefully you've thought about this, and we can break this down into small cubes if you like, and you could look at this and say, right, each of these small cubes that I've looked at now has a side of 1 centimetre, which means that each of these small cubes is going to have a surface area of 1 centimetre squared, because it would be 1 times 1. And if we've got 6 sides with 4 squares on each side, there's 24, which means we're going to have a surface area of 24 squared. Now, we might be given a shape that's not quite so nice with the numbers, so what we can look at is each side. Each side is 2 centimetres long, so 2 centimetres by 2 centimetres gives us an area of that square of 4 centimetres squared. And as we said, there are 6 sides, so the total surface area is 6 times 4 centimetres squared, which will be 24 centimetres squared. Apologies that the formatting has gone a bit strange there. So now that we've done that, let's think about what we did with the jelly cubes. If we were to cut that larger 2 centimetre cube in half in all directions, we now have 8 cubes that are 1 centimetre. So again, I'd like you to just pause and calculate what the total surface area of this volume is now. We've got the same amount of mass each time, but what is the surface area now we've cut it up? So each side that I've highlighted in yellow will be 1 centimetre times 1 centimetre. So that yellow square has a surface area of 1 centimetre squared. There are 6 sides on each of the small cubes. So each small cube will be 6 times 1 centimetre squared and will have a total surface area of 6 centimetres squared per small cube. And there are 8 small cubes, therefore 8 times 6 centimetres squared will give us a total surface area of 48 centimetres squared. So you can see by cutting it in half in all directions, we have doubled the surface area. And if you think about what we said with concentration, the more particles that are present and available for collisions, the more frequent those successful collisions will be. And the more frequent successful collisions we have, the faster the rate of reaction. So a little bit of a copy and complete now. This is fairly simple, but I just want you to make sure you've got some notes written down. So I think that 5 grams of calcium carbonate as a big lump, small pieces or powder, choose the right one, will react fastest because, and then I'd like you to complete the sentence making sure that you use the sensible collision theory terminology that we've been using so far. So pause the video and copy and complete. So I'm very hopeful that everybody here has gone with 5 grams of calcium carbonate as a powder. So what we've got here, we've got diagrams at the bottom, and we've got 5 grams of calcium carbonate, which is often called marble. Calcium carbonate can also be chalk and limestone, but marble is quite commonly used in science for these experiments. So 5 grams of marble as one big lump. Then we have 5 grams of calcium carbonate as small pieces, and then 5 grams ground into a powder. Now we have the same mass of calcium carbonate each time, so there's approximately the same number of atoms of calcium, carbon and oxygen. So that's really important to bear in mind. We can only compare surface area if we're comparing the same mass of substance. So for the same mass of substance, 5 grams of calcium carbonate will react most quickly as a powder. And that's because the powder has a larger surface area, so there will be more frequent collisions between the reactants. Can you spot my mistake in that sentence? Well, the mistake would be that I need the word successful. So more frequent successful collisions would be preferable. Now, I've completely forgot that I put some animations on here, so we do have some bubbles. We will be able to see these reactions happening more quickly because we've got gentle bubbling on the first, sort of slightly more vigorous bubbling in the middle, and then much more bubbling going on the right hand side. Because we have the same mass of calcium carbonate in each beaker, the total volume of gas that would be given out by each beaker would be the same eventually. We would just reach the volume of gas more quickly on the right with the powdered calcium carbonate than we would with the left. And you can see that's because the gas is being given off more quickly from the powder. So I've got just another quick animation here to show you one of the ways that we can test this. So when it comes to measuring rate of reaction, there are a variety of things that we can look at that we've mentioned already. So on the previous slide, we could look at how quickly it takes for the reaction to stop. So how long does it take for the bubbles to stop being formed? Another thing that we could do is to look at the change in mass, and this corresponds to the amount of gas being given off. As the calcium carbonate reacts with hydrochloric acid, carbon dioxide gas is formed, which escapes. And that means that it's given off as a gas and it is no longer present in the reaction solution. Those bubbles of gas contain atoms that are escaping from the calcium carbonate. They're being released. So we could do this reaction in a conical flask because we can put some cotton wool in the top to stop spitting. We do this in a conical flask placed on an electric balance, and we would time the reaction over a period of time, measuring the mass at each sort of period that we pick. This is every minute for 7 minutes. And that would allow us to see the reaction progression. So what I'll do is I'll press next. Okay, so the marble goes in. And as I said, normally we would put a piece of cotton wool in the top just to prevent any spitting and loss of mass due to the reagent mixture escaping. We can see the gas being given off. And as time passes, what happens is the reaction slows down. And by the time we get to the end, what we'll notice is that the two final results are actually exactly the same as each other, and that shows us that the reaction has stopped. Now, the decrease in mass in the first minute, half a gram was lost. In the next minute, 0.6 of a gram, but then it was 0.4 of a gram, 0.3 of a gram, 0.1 of a gram. So it slowed down. As each minute progressed, the reaction got slower. And that will be because there were fewer acid particles present in order to collide. So we're going to have a look at a practical just now. And this is actually a required practical for this topic. The practical you looked at last time with the disappearing cross is also a required practical, but we're going to come back and look at that in a bit more detail at a later date. But we're going to carry on looking at the reaction we've been talking about today already, the marble chips reacting with acid. And you can see the word equation on the screen. Calcium carbonate plus hydrochloric acid forms calcium chloride, water and carbon dioxide. Now calcium carbonate has the chemical formula CaCO3. That is a chemical formula you need to know. Hydrochloric acid is HCl. What's the formula of calcium chloride? Have a think back to our lessons on ionic formulae. Well, it might be very tempting just to say CaCl, but we need to remember that calcium is in group 2, and forms a 2+ ion, whereas the chlorine is in group 7 and will form a 1- chloride ion. And therefore we need 2 chlorines for every 1 calcium 2+ ion. Water, hopefully you know, is H2O, and carbon dioxide is CO2. Now if we look at this equation, we can hopefully see that this is not balanced at present. If you count up all the atoms on the left and on the right, you'll notice that mass is not conserved. Now what I mean by that is if we added up all of the masses from the periodic table for every atom on the left, we would find that it is less than on the right hand side. And that is because we have got 2 chlorines on the right hand side, but only 1 on the left. And we've got 1 hydrogen on the left, but 2 on the right hand side. And that can't happen. We can't magic atoms from somewhere. So what this is showing us is that we need 2 hydrochloric acid molecules to start this reaction to give us enough hydrogens and chlorines to make the products. Now, one of the ways that we've already looked at to measure rate of reaction is to see how quickly gas is produced and measure the mass as it decreases. But what we can also do is to measure that gas as it is given off. And this is a much better way than just saying there are more bubbles being produced in one beaker than the other, actually collecting the gas. And one of the bits of equipment that we can use is on the screen at the minute. This is called a gas syringe. Now when the reaction takes place, the gas is given off by the marble and it goes up through the delivery tube, which we can also label, if I can spell. Let's get the rubber out. So let's try that again, delivery, which is sealed by a bung. And the gas travels up the delivery tube and is collected in the gas syringe. Now we start off with the gas syringe as close to this end as we can. And as the gas goes into that gas syringe, the plunger of the syringe is pushed outwards and it enables us to measure the gas being produced. And if we measure in set intervals as shown on the table that we've got just here, then it enables us to get a really clear idea of what's happening with the rate. So what I'd like you to do is to pause the video just here, copy down the equations, the labelled diagram and the table ready for the next slide, and then I've got a simulation of the experiment to show you. Okay, so we're going to have a look at this simulation. It is one that I've made, so it's not perfect, but it does give us a good idea of what we'd be looking at. Now, the first thing I want to point out is that we would need to clamp this gas syringe, and that is because we need it to be horizontal. If we have the gas syringe tipping upwards, then the plunger is going to be working against gravity and it might end up going out a bit slower than it should. And if we had the gas syringe tipping downwards this way, then the plunger is going to be encouraged by gravity and it might actually go out a little bit quicker. We've also got to start this, as I've already mentioned, as pushed in as far as it possibly can go. So we've got the plunger pushed in to basically where it says 0 on the scale. We've already got the hydrochloric acid in the conical flask. And what we need to do with this, if we were doing this practical, is you have to make sure that you put in your solid reactant, in this case the calcium carbonate, at the same time as putting the bung with the delivery tube on the top of the conical flask and also pressing start on the stop clock. So you kind of need 3 pairs of hands to do this. The reason that's important is that if you put the marble chip in and then you don't put the bung on, gas is going to be produced as soon as the acid touches that calcium carbonate, and that gas might be lost, which means that it's not being collected in the gas syringe. And also, if we don't press start at the right time, then we're going to be not measuring it correctly. So I'm going to press start, and what you'll see is the bung goes on, gas is given off, and the plunger starts going out, and the stop clock goes up. So you've got to keep an eye on all of that, keep an eye on the stop clock, and when the time matches what it says on your table, you need to be writing down what the volume is on the gas syringe at that point. So we're going to start in 3, 2, 1. and the reaction has finished, we can see that the gas has stopped being produced. There's no more bubbles coming out of that calcium carbonate, and the plunger has stopped as well. So we'd stop at 30 seconds. If you need to watch that again, just press rewind by a minute or so to double check that you've got the right figures, and then carry on. So let's have a look at the results for the practical then. When you have been going through this, you should have got 0 at 0 time, 20 at 5 seconds, 35, 50, 60, 65 and 65. And you'll notice here that we've got 65 twice. Also, what you should be able to see is that it goes up quite quickly at the beginning from 0 to 20 in 5 seconds, but from 5 to 10 it only goes up by 15 centimetres cubed. By the time we get to 20 seconds, in 5 seconds it only goes up by 5 centimetres cubed. So on the right hand side we've also got the results for small pieces, which obviously I didn't show you, but just make sure that you've got that. If we were to plot a graph of this information, then we would be able to see these shapes shown on the screen. I'm going to add lines of best fit in for both of these, nice smooth curves again, and we can see the red line is the powder and the blue line is the large piece of marble. Now what I'd like you to do is to sketch this graph in your book. You don't need to put the time labels or as in the numbers. You don't need to put the numbers on. You do need to label the axes as time and seconds and gas produced in centimetres cubed. But a sketch graph doesn't need to have numbers on it. But make sure you've got the lines labelled. Then press play when you're ready to move on. So what I'd like you to try and do is to write a conclusion for the reaction. Think about what we've said about surface area and how it affects rate of reaction. Think about collision theory. Now a conclusion is saying what the results show and why, and that means giving scientific reasons. So pause the video, see if you can write a conclusion, and then press play and I'll go through what I would say. So a conclusion for this reaction could be that cutting the same mass of solid reactant into smaller pieces increases the surface area. This enables more collisions to take place between the reactants, resulting in more successful collisions with energy greater than activation energy and therefore a higher rate of reaction. Now again, I am going to correct myself. What can you notice and what do I need to correct for this particular conclusion if this was an exam answer? Well, I've missed one word here, and this time the word I've missed is frequent. So that phrase, more frequent successful collisions, is really, really important. You can't just say more frequent collisions, you can't just say more successful collisions, you need to be talking about the frequency of the successful collisions. Now to finish off, we're just going to have a look at a few different exam questions that could come up on this kind of thing. So here's our graph again at the bottom right. A very simple exam question for this could be, describe the trend shown in the graph for powder, and that might be worth 2 marks. Now the command word describe means say what you see. It's a very basic command word. So have a think about what you might say for 2 marks for this question. Pause and have a go at writing an answer. Now, because this is a 2-mark question, we would need to be making sure that we say 2 separate things. And if we look at this graph for powder, which is the red one, we can see that it goes up quite steeply and then it ends up tailing off. And if we describe what we're seeing, that's what we'd say. As time increases, volume of gas increases. Now, one thing just to point out is that if you're asked to describe a trend, you always have to make a link between what is on the x-axis and what is on the y-axis. And that's what we are saying for describing a trend. As x changes in this way, y changes in this way. So as x increases, y increases, but use the labels from the axes. Now, the second mark needs to be mentioning about the fact that it plateaus, because as time increases, volume of gas increases could be describing a trend that is directly proportional and just keeps going and going and going. So what we need to say is until 20 seconds when it remains constant. Now you'll notice there that I'm using data from the graph because that's the time that it actually does become constant. So include the data. Second question that we might look at here, explain the trend shown in the graph for powder. So have a think, how is that a different question than the previous one? Describe the trend shown in the graph for powder. Well, a question asking you to explain is asking you to give reasons why. So we're having to say because, we're having to say describe, we're saying what happens and what is the trend, but we then need to say why, we need to say because. So we'd be saying the trend in the graph is, and then the second part of the question is because we need to explain it. Now this would be perhaps 3 marks compared to the 2 marks for the previous question. So pause, have a go answering the 3 marker, and then press play for the answer. So as it is describe and explain, that's what explain takes into account. Explaining the trend, we need to state the trend first. So this is the same as the previous question. As time increases, volume of gas increases until 20 seconds when it remains constant. But then we have to give a reason for why it remains constant. And I would say as the reaction has finished. So it remains constant because no more gas is being produced. So we could say that no more gas is produced for the 3rd mark. Or we could say a reactant has been used up, and that would cause, therefore, no gas to be produced or the reaction to finish. So just make sure when you do an explain question that you give that final because, and you give a reason for why you're seeing that trend. Now the final question is this slightly longer one. Use the results shown in the graph as well as your knowledge and understanding to compare the reactions between HCl and powdered marble and HCl and one large piece of marble. 6 marks. Now this is something called a levels of response question, and you have to think through your answer first. You need to be talking about the reactions for both lines, and you need to be comparing them and talking about why they are similar and why they are different. Now also, because we're talking about a 6 marker, we need to be giving reasons as well. So have a pause and then press play when you're done. So just to give you a little bit of background behind these 6 markers, they are marked as levels of response. It is not a case that you say 6 things correct and you get 6 marks. To get 6 marks, you have to get your answer as a level 3 answer. And this is a general mark scheme. Relevant points, reasons and causes are identified, given in detail and logically linked to form a clear account. Now, logically linked means that you've got to be thinking this through and your answer's got to make sense. It's got to progress from one idea to another. It can't just be random facts in any old order. So for a level 3 answer, we'd be looking for mentions of both HCl and powdered marble and the lump and HCl. We'd be looking for similarities and differences. All of those things have to be included. Now 5 or 6 marks is all to do with whether or not your answer is clear, coherent, logical, makes sense, and also about your quality of written communication. If your quality of written communication is poor, then you'll be knocked down into the 5 marker instead of the 6. Now if you don't quite get into level 3, you might write a level 2 answer. Relevant points are identified and there are attempts at logical linking, but the resulting account is not fully clear. And that would be 3 or 4 marks, with again the 3 mark being given if you've not been particularly logical, if you've made errors within that level. For 1 or 2 marks, we'll be looking at level 1. Points will be identified and stated simply, but their relevance is not clear and there is no attempt at logical linking. So for this question, you might say the powder reacts faster than the large piece. Now that's stating a simple correct fact, but it's not really relevant why we're saying that. We've not mentioned the graph, and there's no attempt at saying why that is. There's also not comparing anything more than just the fast or slow, so it can't be more than 1 or 2 marks. Now if you don't say anything relevant to comparing the reactions, you get no marks, unfortunately, and that's the same for all of these questions. Now on a mark scheme, as well as the levels also be given, will be some indicative content, and this is what the examiners are looking for to be included. So indicative content for this could be that powder has a faster rate of reaction or a shorter reaction time. We can see that there's a steeper gradient which tells us that, and it's because there is a larger surface area and more frequent successful collisions take place. So that's me commenting on the shorter reaction time. I've used the graph, I've mentioned the gradient, and that's really important because the command word is use the results. So I've said steeper gradient, and I've given reasons behind it. So I've made a logical, coherent connection between those. Now that's not all of the comparisons I could make, so I'd need to look for more. Now, something I could mention is that there was the same mass of marble or same volume of gas. Now, how can I tell that? And that's because the reactions produce the same amount of gas. Both of these reactions produce 65 centimetres cubed. Again, I'm using the graph to give me that information. Something else I could mention would be that both reactions reached completion or finished. How can I tell that? Because the results plateaued. So 6 markers are a bit difficult. They're difficult to mark, and examiners are given examples and do a lot of discussion. So what I'd like you to do is to upload your answer to the 6 marker, and I'll have a look and see how you did. I won't necessarily give you a mark out of 6, but I'll be able to give you some pointers. And what we'll do is we'll move on to the next part of the topic next lesson. Send me a message if you have any questions or need any help.